Hey you guys, welcome to this lesson. We are in chapter 7, section 4. We're going to talk today about geometric sequences and series. And make sure you're taking notes in your books. I think it starts on page 379. If you don't have your book, you can take notes on a piece of paper, but I will be checking in the notes as your homework assignment for today. So when we talk about geometric sequences, here's kind of an example. If you think about a pendulum, when a pendulum swings, and there it goes swinging, it's going to swing through a shorter arch each time, assuming there's no additional force. So if the length of the first swing is some distance, then the second swing might be like 95% of that, and then the third would be 95% of that, and so on. And so this list of numbers can be defined as a geometric sequence because we can find the length of each swing by multiplying the previous number by the same value. So for sequences, let's first talk about what a sequence is before we talk about geometric. A sequence is just a set of numbers in a particular order. Each number is called a term. The first term we would call a sub 1, then a sub 2, and then all the way to a sub n. The sequence is finite if there is a finite or limited number of terms. And it's infinite if it continues without end. So you'll often see like a dot, dot, dot. That means it keeps going infinitely. In words, a sequence is a function, and the domain of that function is natural numbers, 1, 2, 3, 4, 5, so on and so forth. And the range is real numbers. So we don't have to deal with imaginary, that's good. And so in symbols, we would say the domain is 1, 2, 3. So for instance, for this finite sequence, the domain, the first term is 4. The second term is 8. So the domain is the number of the term, and the range is the actual term itself. A1, A2, A3. So for this, the domain is 1, 2, 3, 4, but this keeps going, so it's all natural numbers, whereas here the domain and range are limited. In this case, we would say the domain is all natural numbers, which is always going to be all natural, or like the set number in this case, 1, 2, 3, 4, 5, since there's only 5 terms. Now in this case, we would just give the terms, but here we would write this in our set builder notation. So the range is y, such that, remember this means such that y is a multiple of 4, we could say it that way, or we could, y is a multiple of 4 when y is greater than or equal to 4. So basically multiples of 4. Now there will be other ways we will write this after we finish this section. Oop, missed something. Now you can always watch these videos in like 1.5 or 1.25 speed to speed it up a little, or you can even slow it down if it's too fast for you. If you don't know how to do that, Google it or ask me, and I can let you know for the next time. Now, one type of sequence that we're going to study in this section is a geometric sequence, and each term is determined by multiplying the previous term by some constant, and that value of the constant is called a common ratio. Now, the nth term of a geometric sequence is given by this formula, and all that means is this: if I know what the first term is, and I know that the ratio is like 3, let's say the first term is 3 and the ratio is 3, so 3 times 3 is 9, times 3 is 27, so on and so forth. Well, what if I want to know the 100th term of this sequence? I don't want to have to write out all 100 terms, so we can use this formula to find any term in that sequence. If I want to know the 100th term or the 50th term or the 10th term of that sequence, we can use this formula. And all we need to know is the first term and whatever that common ratio is. This is what we call an explicit formula, because if I just want to find like the 100th term, I just plug in 100 for n. If I want to find the 10th term, I just plug in 10 for n. There's another type of formula called a recursive formula, and this type of formula is based on the preceding term. So this is the same geometric sequence formula, but in recursive form. And notice the difference here. Here we have a1 and then r to some power. But here we have r, our ratio, times an minus 1. So think about this. If I want to find the 100th term, a100, then I would have to multiply the common ratio times the 99th term. 100 minus 1 would be 99. So all this is saying is that we would need to know the previous term in order to find the next term. And that's what our recursive formula is. So explicit formula, I can find the 100th term without knowing any other terms. Here I would need to know the 99th term to be able to find the 100th term. Now, another term we'll come back to is geometric means, and these are just the terms between any two non-consecutive terms in a sequence, and we'll talk about that more in a little bit. But first, let's be able to identify if a sequence is geometric. So really all we have to do, is there a number that I can multiply? 2 times what is 6? That's 3. But is that the same thing? 6 times 3, does 6 times 3 equal 15? No. Another way we can do this is to divide terms. So like if I take 6 divided by 2, that's 3. But if I take 15 divided by 6, that's 2.5, and 30 divided by 15 is 2. So this is not a geometric sequence. However, if you think about it, 5 times what is negative 10? And that is negative 2. Is negative 10 times negative 2 20, and so on and so forth? Well, again, if we divide these, we will see that if we divide each of these, we get negative 2. So this one is, in fact, a geometric sequence. So first of all, you need to be able to identify if it's geometric. Then the other thing we'll do is graph geometric sequences, but it's just as simple as graphing points. So if I want to graph the first 6 terms of this sequence, negative 1, negative 2, what's my common ratio? And we can find it by either thinking, what do I need to multiply to get here, or just divide a term by its previous term. Negative 4, negative 2 divided by negative 1 is 2. Negative 4 divided by negative 2 is 2. So this is my common ratio. So if I take that third term and then multiply that by negative 2, or excuse me, by 2, by 2, by 2, then now I have the first 6 terms of that sequence. So if I want to graph it, remember the domain, since it's the first 6 terms, the domain is 1 through 6. The range is just the terms themselves, and then you just graph those points. So this graph looks like this, kind of like a inverted exponential graph it looks like, or a reflected exponential graph. So that's all you're doing, is just finding the terms. It's basically just finding the next 3 terms of the sequence, but then we graph it as well. To find the nth term of a sequence, we'll have to use the formula. So let's see here. Let's do this first. So if I want to find the nth term of each geometric sequence here, again, first of all, I need to find the common ratio. What am I multiplying by in each case to get the next term? And that is negative 3. If I divide 27, negative 9 divided by 3, 3 divided by negative 1 is negative 3. And then here's our formula. So we're going to put it all in the formula. The first term, a1 is negative 1, r is negative 3, so you're literally just plugging those in for a1 and r. And here's our formula for the nth term. So now, how is this helpful? Well, what if I wanted to find, like I said, the 50th term of this sequence? Then all I have to do, instead of writing out multiply by negative 3, by negative 3, and by negative 3 50 times, I can just plug in 50 for n here, and that will give me the 50th term of that sequence. Again, if I know a8, this time they don't give me a1, but they give me r2, r is 1/2. Then in this case, if I want to find the nth term, okay, then we will still use this formula. But in this case, we don't know a1. I do know one of these terms, however. So I'll plug in the term I know, and that term is the 8th term, so we'll plug in 8 here for n. So notice that the 8th term, a sub 8, we would plug in 8 here. So I know everything except for a1. So simplifying and solving this equation, this is 1/2 to the 7th, which is 1 over 128. And then we can multiply both sides by 128 to get what a1 equals. Now that we have a1 and 1/2, our ratio, now we'll just plug them in to write the equation. So that's all you're doing when writing the equation. Start with our formula. As long as you know a1 and r, plug them in. That's the equation for the nth term. If you don't, you can do something like this here. Whatever term you do know, plug in all the variables and solve for a1. Now, we said before that there are recursive and explicit. So the ones we just looked at are explicit formulas. And this right here, what we're given here, is a recursive formula. It's based on knowing the previous term. But we are given the first term. And in this formula, so here's our recursive formula. R is this number in front. So R is 1/5. So we have a1 and we have r. So we can plug this into the explicit formula that we just looked at here, 5 and 1/5 to the n minus 1. So again, how this is helpful, this formula is good if I know the previous term, but if I want the 100th term, I would need to know the term, the 99th term, to be able to find the 100th. Here I can find the 100th term without knowing what any of the other terms are, as long as I know these two, okay? Now, if I'm given the explicit formula, I should also be able to write the recursive formula. And all we need for the recursive formula, so here's our recursive formula. The only thing we need to know for the recursive is r. So for the explicit, we need a1 and r, but in the recursive formula here, we just need r. So if this is the explicit formula, r is 7 right here. This is a1 and this is r. So a1 is 2/3, r is 7. And all we have to do now is plug in 7 for r. So those are the two formulas that you'll need to be familiar with. The explicit, which is, where did it go? Right here. And the recursive, which is right here. And again, to write either of those, you either need a1 and r, or just r. So once you have those, and once you can find those from the previous formula, you can write the other one and vice versa. Let's see, what else are we gonna do? The last thing I think for this part of the video is finding geometric means. So when this says find 4 geometric means between 243 and 32, what that means is this. 243 is one of the terms of my sequence, and I want to find the 4 terms between that and 32. So the 4 geometric means are basically just the 4 terms between 243 and 32. And sometimes they might ask for 4 or 2 or 1. But geometric means are just terms in between terms of a geometric sequence. So in this case, if you think about it, if I think of this as my first term, then 32 would be my 6th term, wouldn't it? 1, 2, 3, 4, 5, 6. So I'm going to use this formula here, and I'm going to plug in what I know to help me find what r equals. If I say that 32 is my 6th term, 243 is my first term, so be careful here since they put this first. This is the first and this is the last. And I don't know what r is, but I know that 32 is the 6th term, so I can plug in everything else except for r. So again, we're going to solve this equation for r. So now if we just divide both sides by 243 and then simplify this, how do we solve an equation like this? If it's r to the 5th, remember that we would take the 5th root of both sides of this equation. And you have calculators. Your calculators can help you. Just plug in the 5th root of 32 over 243. The other thing we can do is raise this to the 1/5 power. So that's another way you could plug that in. 32 over 243 raised to the 1/5 power, if you can read that. And then when we do that, we get that r is equal to 2/3. So that means that my common ratio is 2/3. So now if I want to find the two values in between 243 and 32, then all I do is take 243, multiply it by 2/3. That's the one of them. Multiply by 2/3, multiply by 2/3, multiply by 2/3, multiply by 2/3. And here are my 4 geometric means in between 243 and 232. So let's see, maybe we can do this one as another quick example here. Ooh, you're letting me work on this. Okay, so let's just look at another quick example here. This is question 1 of 6. Determine whether each one is geometric. So am I multiplying 2 times 2 is 4? Is 4 times 2 16? Nope, so not geometric. 11 times what? Well, here it's kind of hard to tell. So we could do 2 divided by 11. Is that going to be the same as 4 11ths divided by 2? And 8 over 121 divided by 4 over 11? And in that case, the answer is, it actually is. So, let's see here. Next question. I'm not going to go through all of these. This is going to take too long. Anyhow, you guys have all the previous examples to look back at. If anything doesn't make sense, go back and watch that part again. But we will also be going over this in class as well. So that is your start on geometric sequences. Make sure you have some notes because those will help you as you work through problems in class. All right, talk to you later.